Okay, so in this video, I'll show you how to generate a PDA from context-free grammar. So let's imagine that we are using this context-free grammar to generate this. So what would be the steps to do that? So the first step that you would do is you would create the Q start, and then after that you would do the first series of transitions. So the first one is that you will ignore the input and ignore the stack, and then push on to the stack, the $sign. And in the second transition, you will ignore the input, ignore the stack, and then push onto the stack the variable s. So let's say here we have s, a, capital T, b, and b, and then we also have t and T, capital T, A, and then empty string. So this is our start variable. So this is why this one is capital S. If this was anything else, so if you see here, this was anything else other than S, then this would be that. So if this was A, then this would be also A. So this has to match this. Okay, and then we go to Q loop, and we start doing each one of the variables that we have. So we're first going to do S, and so we're going to introduce this one loop here, and that is just simple terminals, and we're going to introduce here another loop that has a number of states that it has to go through. So this one for S, so we have to first go to S, and what we're going to do is that if we read on the stack S, which means that we're going to ignore the input, and we read on the stack S, so we want to pop S, and then what we're going to do is we are going to push into the stack this value, and we're going to push first B, then T, then A. So we're going to push B, and then here we are going to ignore the stack and the input so that we can push the other one without anything else happening. So it's going to be empty with empty, and we're going to push T, and then we are going to perform another transition and go back to the loop. So this one is going to push the last one, which is A, onto the stack. So in this case, if we read S here, then what we're going to do is we're going to push B first, then T, then we're going to push A. So this completes this. And so on this side, now I can add the simple S placing B on the stack by ignoring the input, reading S from the stack, and then pushing B on the stack. So that would represent the OR here, this side. Okay, so now we want to represent T. So when we represent T, we're going to represent this one and this one. This is a simple representation that does not need more than one transition. This one needs two transitions. So we are going to establish a loop for T. So we're going to have T first go to a state, and we're going to read, in this case, T in this transition over here, this transition. So we're going to read T from the stack, and then we're going to push A. So like we said, we push in reverse. So this one will be pushed after reading T immediately, and then in the second transition, we will just push on to the stack T, which is the second representation, which is this one. And this one is a simple representation, so we can use this same loop and reuse it and say, okay, in case T, then we also do nothing to the stack. Okay, so now that we finished all the variables, we have a couple of things that we need to do, which is for terminals. So the terminals that we have are A and B. So for every terminal, we match the terminal with itself and do nothing to the stack. And so we do this for every terminal. And that way we are done with this representation. So this is how we manage all variables, and this is how we manage all terminals individually, like A and B, which is part of the alphabet. And then what we are left with is to move to the accept state. So to move to the accept state, I would have here Q accept, and we would have empty string, meaning we're ignoring the input, and then we pop the $, and then we don't do anything with the stack. So this is always the same. This is always the same. Q loop is always present here. This matches this, and these loops are based on whatever we have here. So whatever I give you here, this is going to remain the same, this is going to remain the same, and here's where you need to make a decision on how to manage that. So these are all possible options, which is we have more than one thing to push on the stack, so it's going to look like this, or we have one thing to push on the stack, so it's going to look like this, or there are terminals, and this is how we handle the terminals. And so this is basically how you handle every possible situation that you may have in a context-free grammar that you want to convert to a PDA. So the questions that may come in this case are convert a context-free grammar to a PDA, or design a PDA from this context-free grammar. And so anything that is asked to provide an equivalence of a PDA for a given context-free grammar. So this is the type of questions, and that's it.